Students, today let us see the topic of units and dimensions. So first of all, we should study what is meant by physical quantity. So any quantity that can be measured, we can call it as physical quantity. So length, mass, time, temperature, volume of a substance, all these we can call it as physical quantity. So what is meant by measurement? How can we define this one? So comparison of unknown quantity with a known quantity is called as measurement. So we should have a well-defined known quantity. With that quantity, I will compare the unknown quantity whose physical dimensions I want to calculate. Then such type of comparison itself is called as measurement. For example, here I have a scale or any long rod whose length is L. And if I take another long rod whose length is unknown here, then what I do, I try to compare these two lengths of these rods. Then if I got that this length is equals to 2.1 L, then this measurement itself is called as comparison, or this comparison we can call it as measurement. So this is called as measurement. So now let us see what is meant by unit. So any well-defined standard of measurement, well-defined standard of measurement is called unit. For example, if I write length is equals to 5 meters, then we know exactly what is the meaning of 1 meter. So 5 meters means in comparison to 1 meter, this particular body has a length of 5 times of that meter. So here meter is well defined, and this meter we can call it as the unit. So next we can study types of physical quantities. Types of physical quantities. So physical quantities, we can derive them into two types: fundamental quantities or fundamental physical quantities, and second one is derived quantities. Fundamental quantities means these quantities does not depend on any other quantity. For example, if I want to measure length of this pen, so length of this pen doesn't depend on other dimensions or other physical quantities of this pen. It doesn't depend on mass of this pen. It doesn't depend on density of this pen. So such type of physical quantities we can call them as fundamental physical quantities. And there are 7 fundamental physical quantities. Let us see what are them. They are length, mass, time, temperature, electric current, amount of substance, and finally intensity of light. So these are the 7 fundamental quantities which we have. So all these derived quantities, they depend on these fundamental quantities. For example, if I want to measure volume of any substance, then I know volume is equals to length into breadth into height. So length is a type of length, breadth is also length, height is also a length. So it means volume is depending on the fundamental physical quantities. So such type of quantities we can call them as derived quantities. So after this, let us see the principal system of units. We will see the principal system of units. So in the principal system of units, that is, units are defined in how many types? So that first one we can call it as FPS system, second one is CGS system, third one is MKS system, and fourth one we can call it as SI system. So FPS, foot, pound and second system. Length is measured in foot, mass is measured in pounds, time is measured in seconds. Here C represents centimeter, G represents grams and S represents seconds. Here length is measured in meters, mass is measured in kilograms, time is measured in seconds. But if you come to SI units, we have 7 fundamental quantities and 2 supplementary quantities. So let us see. So here we have 7 fundamental quantities plus 2 supplementary quantities. So 7 fundamental quantities already we have defined: length, mass, time, temperature, electric current, amount of substance and intensity of light. So now let us see the 2 supplementary quantities which we have, which are defined in SI system. So out of the 2 supplementary quantities, the first one is plane angle. Plane angle. So in a circular path, if a person is traveling from point A to point B, then at the center of this circle, he subtends an angle of theta. And if the radius of the circle is r and length of that circular path traced by this person is L, then the relation between this plane angle r and L can be written as theta is equals to L by r. So this is what we call it as plane angle. And plane angle is measured in radians. For one complete circular path, we can say the total angle covered is equals to 2 pi radians, or we can call it as 360 degrees. So this is called as plane angle, and plane angle is measured in radians. Similarly, now let us have a discussion on the second supplementary quantity, which is called solid angle. Now we shall study about solid angle. So instead of the circle which was taken to define plane angle, now we are taking a sphere. Ball is an example of a sphere. So on this sphere, at the top surface of the sphere, we cut a small circular area, and this part of the cone, if you remove from this sphere, then the 3-dimensional area which is formed here, that is called as solid angle. So here I can say this angle theta is a 2-dimensional. But here the angle which is formed at the center of this sphere, this is an example of 3-dimensional angle. So such a 3-dimensional angle we call it as solid angle, and it is measured by the symbol sigma. So if the radius of this sphere is r and the surface area cut is s, then the relation how I can write is, I can write s is equals to sigma r square. So this is the relation between surface area which we have cut and the solid angle which is formed at the center and radius of this sphere. So S is equals to sigma into r square. Now if I separate this cone and draw a separate figure here, then this is how I can draw the figure. Like this I can draw. So the half plane angle which is created, let it be theta, and the total solid angle which is created, let it be sigma. So I hope you are understanding the difference. So half of this cone we are taking only plane angle, that is half a plane angle, and it is called theta. And the total solid angle which is formed at the center of this sphere of this cone, that I can call it as sigma. Then the relation between the solid angle and the plane angle can be written as sigma is equals to 2 pi into 1 minus cos theta. This is the relation. So relation between plane angle and solid angle. So sigma is equals to 2 pi into 1 minus cos theta. Now if you take a complete circle, then at the center of the circle the angle created is 360 degrees. So if total angle is 360 degrees, then I can say the half angle created will be 180 degrees. So if I substitute this 180 degrees here, let us see what happens. Sigma is equals to 2 pi into 1 minus cos 180. Cos 180 value is minus 1. So therefore I can write it as sigma is equals to 2 pi into 1 minus of minus 1 is equals to 4 pi steradians. Therefore, the total solid angle which is formed at the center of the sphere is equals to 4 pi steradians. And the center of the circle, the total plane angle created is equals to 2 pi radians. So this is how we can define radians and steradians. Similarly, if I take this relation, S is equals to sigma r square. So if I take surface area which is cut here is equals to 1 meter square, and radius of this circle to be 1 meter, then if this is 1 and this is also 1, then sigma will become 1 steradian. So this is also another important definition of steradian. So if the total surface area cut is 1 meter square and radius of the circle is 1 meter, then I can say the solid angle which is created at the center of the circle will be equal to 1 steradian. So this is a small discussion on the supplementary quantities which are defined in SI system. Okay. Now after this, let us see what is meant by dimensions. So now we are studying about dimensions. So dimensions can be defined like this. The powers to which the fundamental quantities are raised is called dimension. For example, if you take a derived quantity, any derived quantity will be a combination of fundamental quantities. So in each derived quantity, how many fundamental quantities are present, that we can call it as dimension of that physical quantity. For example, if we take length, distance, displacement, radius, diameter, all of them, they have dimension of length only. So all these physical quantities, they have dimension of L, or we can call it as L power 1. So therefore the dimension of this can be written as m naught L power 1 T naught. It means in all these physical quantities there is no concept of mass, there is no time, so it is having only dimension of length here. Similarly, if we take the dimension of area, then I can say area of any rectangle is equals to L into B, so which has a dimension of L square, or you can call M naught L square T naught. So this is the dimension of area. Similarly, if you take the dimension of any type of area, for example, you take the dimension of area of a circle. So area of a circle, then it has a dimension of pi r square, and here pi is a constant which does not have any dimension, so again it has a dimension of L square, that is M naught L square T power 0. Similarly, if you take surface area of a sphere, then it is equals to 4 pi r square, and 4 pi is a constant. Again, surface area of a sphere has a dimension of L square. So therefore we can say any dimension of area of any type of area, it will have always a dimension of L square. Similarly, let us have a discussion on volume. For example, if I study about volume of a cube, then I can say it is having L into L into L, that is L cube dimension, or I can write M power 0 L cube T power 0. So this is the dimension of a cube. Similarly, if I write volume of a cuboid, then it will have a dimension of length into breadth into height, and again it will have a dimension of L cube itself. Similarly, if I calculate volume of a sphere, then it has the formula of 4 by 3 pi r cube, and here 4 by 3 is a dimensionless constant. So again we have a dimension of L cube, or we can write M power 0 L cube T power 0. So this is how we can understand the dimensions of a physical quantities. So let us see some more dimensions of some physical quantities. For example, density. I can say it is equal to, density is equals to mass divided by volume. So I can write M by L cube. So M L power minus 3 T power 0 will be its dimension. Similarly, if I take linear momentum, then it will have a dimension of P is equals to M into V here. So I can write M into velocity can be written as L T power minus 1. So ML T power minus 1 will be the dimension of momentum. Similarly, if I write angular momentum, so which is represented by L is equals to mvr. So this is one of the formula for angular momentum. For this one I can write ml t power minus 1 into L. So ml square t power minus 1. So this is the dimension of angular momentum. Similarly, let us see some more dimensions which are very important for NEET and JEE examinations. So I want a dimension of speed and velocity. Both of them will be having same dimensions. Speed is distance by time, velocity is displacement by time. So both of them have dimensions of L by T, which is equals to L T power minus 1. Similarly, let us see the dimension of acceleration. Then it has a dimension of change in velocity divided by change in time, dv divided by dt. So L t power minus 1 divided by t. So L t power minus 2 will be the dimension of acceleration. Similarly, if I take the dimension of force, I can write F is equals to ma. So m into L, or we can write it as dimension of mass is m, acceleration is L t power minus 2. So this is the dimension of force. Now we take the dimension of work done. Work done is equals to force into displacement, or I can call it as Fs cos theta. Cos theta is a dimensionless value. So force dimension is ml t power minus 2 and displacement dimension is L here. So therefore I can write ml square t power minus 2. So this is the dimension of work done, and this is the dimension of energy also. Because the capacity of doing work is nothing but energy. So definitely the formula for energy and work done should be same, and therefore its dimensional equations also should be equal. Similarly, if I take dimension of power I can write it as work done divided by time. So work done is ml square t power minus 2 divided by time. So ml square t power minus 3 will be our dimension. Now if you take the dimension of pressure, so pressure is equals to force per unit area. So force dimension is ml t power minus 2 divided by L square. So ml power minus 1 t power minus 2 will be the dimension of pressure. Now if we take the dimension of moment of inertia, then for a single particle when it is moving around any axis, for the value for that one the moment of inertia is given by I is equals to mr square. So mass into L square, or we can write ml square t power 0 will be the dimension of moment of inertia. Similarly, let us see the dimension of torque. So torque can be written as r dash cross f dash, or you can write it as rf sine theta. So torque can be written as r into f when theta value is equals to 90 degrees. So therefore L and the dimension of force is ml t power minus 2. So I can write ml square t power minus 2. So if we observe carefully, this torque is having a dimension of ml square t power minus 2, which is also the dimension of work done. So work done is also ml square t power minus 2 itself. Now let us see the dimension of surface tension. So surface tension T can be written as force experienced per unit length on an imaginary surface of a liquid surface. So ml t power minus 2 divided by L is equals to mt power minus 2 should be the dimension of surface tension. Now if we calculate the dimension of coefficient of viscosity, here we have a formula F is equals to eta a dv divided by dx. The viscous force between two layers of liquids is equals to eta into the surface area of both the liquids which are touching, and the change in velocity to the distance between two layers of a liquid, that is called as force of viscosity. So here eta I can write it as F into dx divided by a into dv. So F can be, dimension of F is we know ml t power minus 2, dimension of dx is nothing but distance between two layers which is L, a is area of the layers which are in contact which is L square, and dv change in velocity Lt power minus 1. So therefore this L and this L gets cancelled, so I can write it as ml power minus 1 t power minus 2 plus 1. So ml power minus 1 t power minus 1 should be the dimension of coefficient of viscosity. Similarly, let us see the dimensional formula of universal gravitational constant. Universal gravitational constant. So for universal gravitational constant, we have force between two masses, which is called as Newton's law of gravitation. So G m1 m2 divided by r square. So therefore G is equals to fr square divided by m1 m2. So G into, so dimension of force is mlt power minus 2, dimension of length is l square, dimension of m square is m into m is m square. So therefore dimension of G is equals to m power minus 1 L cube T power minus 2. So this should be the dimension of universal gravitational constant. Similarly, let us see the dimension of acceleration due to gravity. So dimension of acceleration due to gravity. So we have a relation for acceleration due to gravity. G is equals to Gm divided by r square, where capital G is universal gravitational constant, m is mass of the body or mass of the planet for which we are measuring the acceleration due to gravity, and r is the radius of that body or radius of that planet. So G is equals to, dimension of G just we have derived, m power 1 L cube T power minus 2, and mass dimension is m divided by L square. So therefore I will get acceleration due to gravity is equals to, these two gets cancelled, so L T power minus 2, or I can write m power 0 L T power minus 2. So this is exactly the dimension of acceleration itself, general acceleration. So this acceleration due to gravity is just acceleration due to gravitational force. So definitely both of them should have the same dimensions. Similarly, if we see the dimension due to gravitational field intensity, then we can write Eg is equals to force experienced per unit mass is called as gravitational field intensity. So force dimension is mlt power minus 2 divided by mass, so Lt power minus 2. So if you observe carefully, so this Eg and this G value, both of them have the same dimensions. That is, numerically they are always equal. And this is one form of defining acceleration due to gravity also, like that also we can say. Similarly, gravitational potential. For this one we can define as, so gravitational potential is equal to, we can write it as V is equals to work done per unit mass. The amount of work which is done to take one mass from infinity to a particular point in the gravitational field of another body, that is called as gravitational potential. So this can be written as ml square T power minus 2 divided by m, which is called L square T power minus 2. So this is the gravitational potential due to gravitational field of the earth. Similarly, let us see some of the dimensions in heat topic. So, if I study about coefficient of thermal conductivity, then I can write Q is equals to Ka into theta 1 minus theta 2 into T divided by L. So this is the formula of coefficient of thermal conductivity, where Q is the amount of heat energy which is traveling from one phase of the body to another phase. K is coefficient of thermal conductivity. A is area of the phases where heat is transferred from one place to another place. Theta 1 minus theta 2 is the temperature between both the phases, and T is the time taken, and L is the distance between both the phases. So from here I can calculate the equation of K. K can be written as QL divided by A, theta 1 minus theta 2 into T. So therefore dimension of K can be written as, so Q is nothing but energy, so ml square T power minus 2 into L divided by area dimension L square, and theta 1 minus theta 2 is temperature difference. So temperature is fundamental quantity, so directly I can write it as theta, and here time taken is T. So therefore this term and this term gets cancelled, so I can write it as ml T power minus 3 into theta. So this should be the dimension of coefficient of thermal conductivity. Similarly, we will study the coefficient of thermal expansion, which is given by alpha is equals to L2 minus L1 by L1 delta T. So therefore, this L2 minus L1 is having a dimension of L, and this one is also having a dimension of L itself. So both of them gets cancelled. So finally the dimension of alpha is equals to T power, that is temperature can be written as theta power minus 1, or I can write m power 0, L power 0, T power 0, theta power minus 1 should be the dimension of coefficient of thermal expansion. Similarly, let us see the dimension of specific heat. So how can we define specific heat? S is equals to the amount of heat required to rise the temperature of a unit mass of a body by unit rise in temperature. So S is equals to Q by M delta T. So Q can be written as ml square T power minus 2 divided by M into theta. So M gets cancelled. So L square T power minus 2 into theta power minus 1 should be the dimension of specific heat. Similarly, we will see the dimension of heat capacity, which is indicated by H is equals to Q by delta T. So H can be written as ml square T power minus 2 divided by theta. So therefore H is equals to ml square T power minus 2 into theta. So this should be the dimension, theta power minus 1. So this should be the dimension of heat capacity of a body. Similarly, let us see the dimension of Stephen's constant. So this is Stephen's constant we will get in Stephen's law, which is called as power is equals to sigma EA T power 4. The amount of energy that is released per unit time of a body whose temperature is T and whose emissivity is A, whose surface area is A, is called as Stephen's law. So therefore, how can I write power? Power can be written as work by time. So ml square T power minus 2 divided by T. So this should be equal to sigma, and emissivity is a dimensionless constant. So sigma into L square into theta power 4. So therefore, sigma is equals to, this can be written as ml square T power minus 3 divided by L square into theta power 4. So L square gets cancelled. So ml power 0 T power minus 3 theta power minus 4 should be the dimension of sigma. Similarly, we can find out the dimension of Wien's constant. So this dimension of Wien's constant we will get in Wien's law, where it says the maximum wavelength of energy released is directly proportional to 1 by temperature. As temperature increases, the wavelength at which maximum energy is released, that decreases. So I can write lambda m into T should be a constant, and that constant we call it as B value. So therefore dimension of B can be written as, dimension of lambda is nothing but L, so L into T should be the dimension of Wien's constant. Similarly, now let us see some of the dimensions in electrostatics. So for example, if we take the dimension of charge, electric charge. then I can say Q is equals to I into T. So Q is equals to, the dimension of Q can be written as AT, because electric current already we have discussed, it is a fundamental quantity. So I can be, dimension of I is A and dimension of time is T here. Similarly, we can see the dimension of electric field intensity. So which is defined as E is equals to force experienced per unit charge. So force dimension is ml t power minus 2 divided by charge can be written as A into T. So therefore, ml t power minus 3 into A should be the dimension of electric field. Similarly, we will study the dimension of electric potential, so which is written as V is equals to work done per unit charge. So work done is ml square t power minus 2 divided by I into T, so which can be written as A into T. So dimension of this one will become ml square A power minus 1 t power minus 3. So this should be the dimension of electric potential. Similarly, we can see the dimension of electric dipole moment. So the dimension of electric dipole moment can be written as P is equals to Q into 2A, or we can write in terms of small a, where Q is any of the charge and A is the distance between two charges. 2A is the distance between two charges. So therefore, dimension of electric dipole moment can be written as AT into L. So m power 0, L power 1, T power 1 into A should be the dimension of electric dipole moment. Next, let us see the dimension of capacitance. So C is equals to Q by V. So this is the formula of capacitance. So the amount of charge stored on plates to the applied potential difference is called as capacitance. So charge dimension is A into T divided by potential dimension, just we have derived here. Potential is ml square A power minus 1 t power minus 3. So therefore I can write it as, so m power minus 1, so L power minus 2, then A power 2 and T power 4. So this is the dimension of capacitance. Similarly, we can also find out the dimension of magnetic field intensity, which is called as B. So F is equals to BIL. This is the relation which we have. The force experienced by a current carrying conductor which is carrying a current I when it is placed in a magnetic field of B and whose length of the conductor is L, then force experienced is given by F is equals to BIL, or we can write ILB. So therefore B is equals to F by IL. So B is equals to F divided by I. Okay, directly we write the dimensions here. So force can be written as, dimension of force is ml t power minus 2 divided by A into L. So m t power minus 2 into A should be the dimension of magnetic field intensity. Similarly, we can also dimension the dimension of inductance. So in the dimension of inductance, we have a relation E is equals to minus L di divided by dt. So therefore E here is nothing but EMF induced, or we can say the potential difference produced. So E is having a dimension of just potential, that is m, this one, ml square A power minus 1 t power minus 3 is equals to L, I can be written as A divided by T. So the dimension of L can be written as, that its inductance can be written as L is equals to ml square A power minus 2 t power minus This A comes to this side and becomes minus 1. So minus 3 plus 1, this becomes equal to minus 2. So this is the dimension of inductance. So what we have understood here is, if we can know the formula of any physical quantity, very easily we can find out the dimensions of physical quantities.